Thanks for joining. We're about to do some practice problems, which is one of the best ways that we have to help us learn. Now, if you haven't tried these problems yourself, please try them yourself first. There's this beautiful button. It's somewhere along here called pause. Make use of it. See the problem? Pause. Try it yourself. Then if you need to, you can unpause, and we can compare answers. In this way, you get engaged, you'll learn, you'll succeed. And that's what we want, your success. Let's get going. Number 1, find the domain of the function. And this function is written in a very interesting way. So it's a function of 3 variables, x, y, z, and involves integrals. Integral x squared to y squared, 1 over 2 plus t dt, and integral z to the 4th to 1 over t squared dt. And we're going to write the equation of the level surface of g of x, y, z passing through the point 4, 1, minus 1. All right. Now, what is domain? Well, that's a great question. Now, domain says, what am I allowed to plug into the function? In other words, what inputs will give us an output? So we tend to avoid certain things. Among the things we tend to avoid is things that involve division by 0, and it looks like there's some divisioning happening, so you got to be a little bit careful to see what's going on. Now, we always are allowed to rewrite our function if that will help us understand things better. And I think we're in that case here. So we have integrals involved, but these are integrals that involve functions which are nice. In other words, ones that we know antiderivatives for. So that certainly gives us an edge. So let's rewrite the function. So we have g of x, y, z is equal to, and I'm just going to copy it down again, x squared to y squared, 1 over 2 plus t dt plus integral z to the 4th to 1 over t squared dt. Now, what's the integral of 1 over 2 plus t? Well, if the 2 wasn't there, integral of 1 over t is like natural log. Now, what does the plus 2 do? Well, it's natural log, right? But you just have to add in the plus 2. You can do it sort of a long ways, which is to say, oh, let's do a substitution. But hopefully you're to the point where you're comfortable enough to say, oh yeah, that's the integral of log of t plus 2. When in doubt, just take the derivative of log of t plus 2, and you see you get back to where you started. How about 1 over t squared? Now, the way you would integrate that is to say, if I have 1 over t squared, well, that's really the same as the integral of t to the negative 2 power. Now, written this way, it's more calculus friendly. Why? Well, because we have t to a power, and there's a nice rule. And so the rule says, that would be add 1 to the exponent, giving us t to the minus 1, and then you divide by that minus 1. And dividing by minus 1 is the same as multiplying by minus 1. So you get minus t to the minus 1 plus c, or we get 1 over t plus c. So we can handle that kind of integral. So what do we have? We have minus, whoops, I forgot my minus there, minus 1 over t, evaluated, these are definite integrals, z to the 4th to 1. So on a side note, what we're doing here is applying the fundamental theorem of calculus. All right, now we're not done yet. We plug stuff in. So we have log of y squared plus 2, subtract log of x squared plus 2, minus, plug in 1 over 1, 1, and then minus, there's another minus, makes it a plus, 1 over c to the 4th. Okay, so we now see in this form, we see logs and division. We don't see a square root. That's the other thing you might have to worry about, but there's no square roots. Remember, can't take square roots of negatives. So let's start with the logs. we can't have a log of 0 or anything less than 0. Well, the good news is when you square a number, it's not negative, it's positive. And plus 2 says you're at least as big as 2. So these log, both of them, they're okay. Not going to be a problem. No need to worry. Here we do have an issue. You see, we have a denominator z to the fourth. Z to the fourth could be 0 if what? Well, it could be 0 when z equals 0. So we're like, uh-oh, potential problem. And the way we often find domain is to say, find your problems, everything but that. So, a great aha, we say that, well, we need z to the fourth to not be 0, or we need that z is not 0. So what's our conclusion? So our conclusion is the domain is all x, y, z with z not equal to 0. Okay. Now, that is this part of the problem. There's still another part of the problem. Write the equation of the level surface passing through the point 4, 1, minus 1. So what do we do? Well, how do you find a level surface? You set the function equal to a constant. And if they specify a point, it's actually pretty straightforward what you need to do. You say, well, you set the function, in our case g of x, y, z, equal to a constant. Which constant? Well, you have to make sure we include this point. So you say, well, plug in the point into the function, and that gives you the right constant. So for us, well, let's go ahead and plug it in. G of 4, 1, minus 1. Well, that would be log. And now we have 1 squared plus 2. So that's log of 3. Minus log. Now here it's 4 squared plus 2. That's 18, right? Yeah, it is. Log 18. And minus 1. And then we have plus 1 over z to the fourth. Okay, well, minus 1 to the fourth is 1. So that's going to make it a plus 1. All right, well, that's good. We can simplify a little bit at the very least. The ones cancel. Pew, pew. You don't have to make the sound effect, by the way, when doing the problem. But doesn't it make it more satisfying? We can even use properties of logs here and do what? Well, we say, hey, we've got a log of 3 minus a log of 18. When you see subtraction, that becomes division. So 3 over 18, using properties of logs, right? Log subtraction becomes division. Really useful fact. Good to know these things. So this is log of 1 over 6. And if you like, right, because 3 and 18, factor of 3, you can even say log of 1 over 6. That's the same as minus log 6. Now, we have our constant. So, we simply write down our answer. And it's the following. So, we take our function, log y squared plus 2 minus log x squared plus 2 minus 1 plus 1 over z to the fourth is equal to minus log 6. And that is our level surface that passes through the point. Now, you might ask the question, well, what makes it a level surface? Well, what makes it a level surface is that we have 3 variables involved. And so we have 3 things that can change, and that turns it into a surface. All right. Well, good times, and that was a lot of fun. Let's keep moving along. Number 2. Sketch and label the level curves for our function f of x, y, y plus 1 minus x squared over y squared plus 1 for the values or heights of 0 and 1. What does it mean by heights? Well, when you think of level curves, what you're thinking of is you have this surface and you're slicing at different heights. And so, in other words, you fix a z value. It's a lot like a topographical map. And so when we're trying to do a slice, we're saying, where are all the points which produce a certain output? In our case, 0 and 1. And then say, okay, what can we do with that information? Well, in our case, we only have 2 things to do, so that's good. But where do we begin? Well, we set our output to 0. So in other words, say f of xy equals 0. Well, what does that become? Y plus 1 minus x squared over y squared plus 1 equals 0. Now, the nice thing is when you have a fraction equaling 0, what must be true? The numerator must equal 0. You can see this if you sort of cross multiply. And so in other words, just multiply the y squared plus 1 across, but then it just disappears. So this really gives us a y plus 1 minus x squared equals 0. And we say, hey, we can recognize that surface because if we move terms across, that becomes y equals x squared minus 1. Okay, good. And what is this? Well, this is a parabola that you've shifted down by 1. I say, aha. We'll even make a note. Parabola shifted down by 1. All right. Well, good. Now, we should have made a comment. We'll make a comment now. Notice, even though we have a division, this y squared plus 1, this will never be 0. So we're not going to have to sort of stress like, oh, what happens if the denominator is 0? Nothing, because it's never going to happen. Life is good. Life is wonderful. Okay, now we have to repeat. 1. Well, what will that do? We have f of xy equals 1. So that becomes y plus 1 minus x squared over y squared plus 1 equal 1, right? Set the function equal to the output. Now, from here, again, do the same process. Clear your denominator. Y plus 1 minus x squared equals, okay, y squared plus 1. I really like to think of this as we're just cross-multiplying, but in general, I say get rid of fractions if you can. Fractions are dangerous. So, okay, we got rid of fractions. We can do a little tiny bit. We can cancel some 1s. And now we look at this and say, there's a particular shape here. We have y squared and x squared, and if we move them around, they both have the same sign. So we're like, circle, because it's going to be a circle. All right, so let's see. We'll move them across, right? So we get 0 is equal to x squared plus y squared minus y. Now, I said circle, but in this format, it's kind of hard to see. You might say, well, there's not even any radius here. Well, it gets worse than that. This is not in the right form. It's not a square. So it'd be nice if we could have a square. It'd be nice if maybe we could complete the square. Okay, so we're going to do a little bit of completing the square, right? Good times. So there's nothing to worry about for the x squared. It's already good to go. For the y squared, we look at this and say, well, I'd like to add something here in such a way that this whole piece became a nice square. And to figure it out, take the term in front of the y. In this case, it's a -1. Divide it by 2, which is -1/2. Square that. and you get a quarter. So this should be a quarter. Now, be careful. If you add something, you've got to balance it out because you've now changed the equation. So you want to say, wait, I want the same equation, or rather, more particularly, I want equivalent to the same equation. So we'll just say we'll add a quarter to the other side. Notice now it's equivalent, but it's better because this part becomes y minus 1/2 squared. All right, so we have x squared plus y minus 1/2 squared equals a quarter, which we can write as 1/2 squared. And that's great. So what is that? Well, so this is a circle. The center, we can read off, is at 0, because this is x minus 0, and 1/2. And the radius is 1/2. All right, so now we have our surfaces. Our curves. We've identified them. We need to sketch them and to label them. So we'll put in our axes here. And what do we see? Well, let's start with our parabola. So we're going to shift down to -1. And let's see. Sorry, I'm just pausing because I want to make sure my picture is big enough. Let's say that was at 1/2. So here's -1. And, all right, so you don't always have to be this precise. So the parabola will go up. Now, if they ask you to draw, they'll actually give you an axis, and it'll be much easier to do these. Okay, so this is the level curve corresponding to 0, so we're going to put a 0 next to it. So that's our label, right? So it says sketch and label. Okay, so that's one of them, but we have to do the other one. Okay, so now 1/2 is here, so this is at 0, 1/2. Radius 1/2 says we're going to come out like so. And we need to label it, and that's a 1. So there's the level curve for 0, and there's the level curve for 1. And we did it. We sketched and we labeled. And so life is good. Aha! Cool. So for these types of problems, what's the process? You set the function equal to the value, figure out what the curve is, and then you sketch. Now, one word of warning. Sometimes you'll have an expression where there's a fraction where the denominator can be 0, and for that they'll turn it into a piecewise function. And if it's piecewise, just be careful of anything that might overlap with the piece where it's undefined. You might have to put in a little hole. But other than that, not much to do for these problems. You get to channel your inner artiste. Good times, good times. All right, let's keep going. Number 3, find the direction of steepest descent at the point 3, 4 for the surface z equals a function of x and y, log of 3x minus 2y plus 4x square root of y. All right, now, what are we doing? Well, we're looking for steepest descent. So the idea is you kind of have the following, is you're on a surface, right? You're on some sort of surface, and you're standing on it, and you're like, okay, which way should I be moving so I'm going downhill fastest? In other words, I want to make it the rate at which I'm going down is as high as possible. Now, there was a key word in what was just said, rate. So when we're talking about finding the direction of steepest descent, it has to do with rates which means derivatives. So this is a problem about directional derivatives. And so that's where we're starting. So, we say, okay, we need to focus on directional derivatives. And we'll get to this in a second here. All right, we'll make this a little side comment. And now, so if we're doing directional derivatives, that means gradient. So let's start with our gradient. So we're going to take gradient of f. And when we take the gradient, that really says we're collecting the partial derivatives. So partial f, partial x, and partial f, partial y. Okay, so we're going to take our derivatives here. And now take the derivative with respect to x. So we're going to treat y as a constant. Well, there's an x here. So whenever I see a log, I remember do a fraction. Downstairs is what's on the inside. And then take the derivative of the downstairs. Well, taking the derivative with respect to x would give us a 3. Here we have an x, just a single x. So the derivative of that would be 1, but we still have the rest of it coming along as a constant. 4 root y, comma. Now, partial f, partial y. Okay, same thing, but now y is our variable. Again, we have a log, so we write our fraction, write the inside in, and then take the derivative of the inside with respect to y, and that would be a negative 2. Plus, well, here we have a 4x. Now remember, square root of y is really code for y to the 1/2. So what are we going to have? We're going to have a plus 4x 1/2 y to the negative 1/2. Okay, that's fine. And we can clean this up if we wanted to. This becomes 2x over square root y. Okay. There we go. All right, now, that's gradient of f. But what do we need? Well, we need to have gradient at a point, right? Because we're at the point 3, 4. So what we now need to do is we need to evaluate. So we're going to do that next. Say, okay, what is gradient of f at 3, 4? Well, this will be, again, it's a vector. Gradients are always vectors, so make sure it's a vector. We'll have 3 over 3 times 3 minus 2 times 4. 9 minus 8. 1. Plus 4 times the square root of 4, which is 2. Comma. Minus 2. 3 times 3 minus 2 times 4. 9 minus 8. 1. And then we have plus, we'll have 2 times 3, that's our x, over square root of 4. So that's a 2. All right. Well, we can clean that up. That becomes 3 plus 8. That's 11, comma. And then we have minus 2. The 2's here cancel. Minus 2 plus 3, that's a 1. All right. So, gradient of f at 3, 4 is 11, 1. Now, what do we need to do? Well, we need to get the direction of steepest descent. We're going to actually talk about this kind of next week. This problem is a little bit too early, but we have almost enough to figure it out. So let's go ahead and just sort of reason through it. And but next week we would look at this and say, there's the answer. All right, so here's our reasoning. Now that we have our gradient of f at our point, we say, okay, we have gradient f at our p dot u. That's our directional derivative in the direction of u. And we say, well, what's the goal? We want to make this very large negative. Negative because we're going down. We're going down. Down, down, down. We're going down. Woohoo! Right? Okay, so what do we know about this expression? Well, dot product. We know dot products. This becomes magnitude gradient f of p, magnitude of u, cosine theta. Well, u is supposed to be a unit vector, so that goes away. This is fixed. So, this part we say, what can we say about cosine theta? How low can it go? How low can it go? Well, we can make it -1. That's the lowest that we can get. All right, so the steepest descent would be the negative gradient. Now, that's the rate. We were asked for the direction. So we're like, okay. So what does that tell us? Well, it tells us we need theta equals pi. But wait, what is our theta? Well, what theta says is we're at this point 3, 4. We have a vector, that's the gradient, and the gradient vector is here. It points in this direction. Right, this is the vector 11, 1. And what we need is that u has to be an angle of pi away. So, well, if you're an angle of pi away, that means that you are 180 degrees. So u points exactly opposite. So that's the great aha. All right, and this is what we'll learn soon. And maybe by the time you watch this video, you already have learned it. But all right, so the great aha is to say, if we want the direction of steepest descent, run opposite the gradient. So we say, okay, the direction of steepest descent is opposite the gradient. Now, when we say opposite the gradient, what does that mean? Or, if you like, that's minus the gradient at 3, 4. So you're like, oh, toss in a minus sign, day done, right? Hold on. So you might say, that means this is our answer. And is it? And why not? It is not our answer. Curses. What's wrong with this? Well, when we're thinking of direction, they really insist on, and so we want to be really careful here, unit vector. Is this a unit vector? No. Has the wrong size. So we fix that. Okay, so we need to make this unit vector. So, okay, that's not a problem. We know how to do that. We just need to scale it. So the problem is it's too long, so we're going to shrink it down. So we do a little quick computation. The magnitude of -11, -1. Well, that's the square root of 11 squared, or well, -11 squared, -1 squared. That's the square root of 121 plus 1. Square root of 122, also known as square root of 122, right? There's nothing we can really do for that. So, how do we now use that? Well, you come in front. 1 over the square root of 122. And now, we're done, right? So opposite the gradient, that's steepest descent, make it a unit vector, divide by the magnitude, and then you have the direction of steepest descent. Okay, and there we go. Whew! All right. Well, we made it. All right. Let's get going. Number 4, calculate partial derivatives. partial g partial y and partial g partial x for the function g of xy is log base 3x of y squared plus 1. And now we're like, well, okay, natural log, big fan. Always have been, always will be. Log base 3x, what? But now, here's a nice fact. So, we're going to do a little algebra fact here. So, algebra fact. And it goes like this. It says, if you have log base b of a, this is equivalent to saying natural log of a over natural log of b. And ultimately what it really says is that all logarithmic functions basically are the same up to a scaling factor. And so what does that let us do? Well, it lets us do the following. It says, hey, you know, if you like natural log, use natural log. You just need to rewrite. So this becomes natural log of y squared plus 1 over natural log of 3x. Now we have something we're going to be more comfortable with. All right. Well, with that, little bit of trickery out of the way, we're ready to go. Okay. So, it's interesting they chose y in front of x. I don't know why. That's, ours is not to question why. Ours is but to take the partial derivatives and get full credit. Okay, so here we go. So we're going to take partial g partial y. And the good news is that part's upstairs. So what is that going to be? Well, we can think of it as, sorry, I'm just hesitating just to help see what happens. I'm going to pull this 1 over log 3x out in front, just so it's in the front. And then times the derivative of log of y squared plus 1, and derivative of log of y squared plus 1. The y squared plus 1 goes downstairs. The derivative of y squared plus 1, which is 2y, goes upstairs. And then if we wanted to, we could multiply these out. So 2y divide by y squared plus 1 log 3x. All right. So that's partial g partial y. Now, the next one is going to be a little bit more interesting. Okay, so how do we do this one? Partial g partial x. Before we do that, let's just make ourselves a note. We can rewrite our function as log of y squared plus 1 times log 3x to the minus 1 power. Okay? That's just another way to write g. So, partial g partial x, the log of y squared plus 1, that's a constant. And now we're going to do the chain rule. Chain rule. It's a great rule. It's a chain rule. So, this is sometimes it's called the power rule. We're going to take that negative 1, bring it down. So there's a negative 1. Then we're going to raise this now not to the negative 1, but to the negative 2. And then we keep going. Times the derivative of the inside. All right, so we took the derivative of the outside, leave the inside alone. Derivative of the inside, okay, log of 3x, so it's a fraction. 3x goes downstairs, and the derivative of 3x goes upstairs. And there we go. Now we can clean all this up, right? You might say, well, sure, you get the cancellation with the 3's, but what else? Well, some other things that we can do is we can, as we went from log 3x to log 3x minus 1, we can also go backward. We'll do that here. We have a minus sign, so we'll leave that upstairs. So we have a minus log y squared plus 1. Now downstairs we have an x. Then we have this term moved downstairs. So that's log 3x squared. And there's our other partial derivative. And double check, make sure you got all the terms accounted for, and we're good. And so there's nothing too surprising as long as you know your algebra. And who doesn't love a good algebra fact, right? All right, good. Well, let's move on. On to the next one. Number 5. The level surface to the 4-dimensional, I don't know why they had to emphasize it, but okay, graph for w equals f of xyz equals 3x minus 2y plus 4z over 5x minus 6y minus z at the point 2, 1, negative 3 is a plane. Find a formula for that plane. Okay, now, you might say, oh my gosh, do we have to sketch a 4-dimensional object? No. What do we have to do? We have to do level surfaces. How do you do level surfaces? Well, it's the same idea as we did for level curves a while back. So what we're going to do is we're going to say, well, we need f of xyz equal to a constant. Now, in this case, they didn't tell us a constant, but they said it's got to have a point. So we say, well, how do we find that? And the answer is we plug that point in. So it's f at 2, 1, negative 3. So we say, oh, okay, so we plug this in. Now f of xyz, that's 3x minus 2y plus 4z, divide by 5x minus 6y minus z. That's got to be equal to. Now plug in your numbers. Okay, so we have 3 times 2 minus 2 times 1 plus 4 times negative 3. Divide that by 5 times 2 minus 6 times 1 minus negative 3. All right, so we just start going through this very slowly. 6 minus 2 minus 12. Divide that by 10 minus 6 plus 3. Okay, yeah, sure. They're numbers, and they do things. So, okay, 6 minus 2 minus 12 would be what? Well, that would be negative 8. And 10 minus 6 plus 3, that would be 13 minus 6, that's 7. All right, now we're getting close. So let me rewrite this again. So we have 3x minus 2y plus 4z over 5x minus 6y minus z is negative 8 over 7. Now, what do? Well, we have fractions. Fractions are not good for us. We're not big fans, or at least I'm not a big fan. So I'm going to get rid of the fractions. I'm going to do it by cross multiplying. And so we're going to carry that out. And what do we get? Well, we're going to get that 7 times 3x minus 2y plus 4z is equal to negative 8 times 5x minus 6y minus z. Okay, so 21x minus 14y plus 28z is equal to minus 40x plus 48y, okay, plus 8z, right? Yeah, you might get some really fun numbers. And now we just start moving things across and see what we get. So we're going to add 40, so that gives us 61x. Subtract 48. 14 subtract 48 will be 62. Yes? Yes, yes. So minus 62y. 28 subtract 8 will be a 20. And we've used everything up. So 61x minus 62y plus 20z equals 0. And there's our formula for the plane. Woohoo! Nice! We should have probably paused and said, can we simplify anything? Are there any common factors? There are not. So we're like, okay, then we're good to go. We're good to go. Woohoo! On to the next problem. Number 6. The law of cosines for triangles. Law of cosines brings me back. Good times. It says c squared is a squared plus b squared minus 2ab cosine c. Now, if you just cover that up, you're like, oh, isn't that like Pythagorean theorem? It is. And so essentially, the law of cosines is like Pythagorean theorem for other kinds of triangles, not just the right ones. All right, anyways, it defines the measure of angle C as, and I feel this is going to be an important phrase here, an implicit function. Okay, so I think this has something to do with implicit functions of the side lengths A, B, and C, and note angle C is opposite of the side having length C. That's not really going to come in. They just threw that in for fun. Find the value of partial C, partial A, when A is root 3, B equals 4, and C is root 7. Now, how do we approach such a problem? Because, well, we have to figure this out, right? It's the problem that's been given to us. Now, what we have here is the following. We have c squared, I'm going to write this down again, a squared plus b squared minus 2ab cosine c. And notice we're going after partial c, partial a. So there's 4 symbols here. Little a, little b, little c, big C. And so what happens is we're supposed to think the following, and we will to a degree, but we're going to even simplify it as we go on. So when we look at this, we say, oh, I have that our big C is really, it's a function of little a, little b, and little c. So I'm going to think of little a, little b, little c as being independent of each other. And now I'm just saying, well, suppose I perturb a little bit. What happens? Now, here's what's going to happen. Notice we have 2 pieces here, C and A. Those are the pieces that we need to pay attention to. So A, C, right? I'm just marking those off. Everything else that isn't marked for partial C, partial A is going to be treated as a constant. And so what does that mean? When we take derivatives, they're going to disappear. Or they're just going to end up being in the front, right? Just depends. So we say, okay, we're taking derivative with respect to A. That's fine, that's fine. And now, because we're thinking of C as depending on A, we're going to do a chain rule type thing. All right, so here's how we're going to proceed. We're going to start by writing our formula down. C squared is A squared plus B squared minus 2AB cosine C. And we're now going to take the derivative with respect to A, right? Because that's what this says. Take derivative with respect to A. We're going to do it to both sides. The only things which are going to have actual derivatives done are the things we've marked. Things with A or C. Everything else gets treated like a constant. So that's going to help narrow it down quite a bit for us. So we say, okay, what's the derivative of C squared? Nothing. It's gone. 0. There's no A involved. What's the derivative of A squared? Well, with respect to A, right, because that has an A, derivative of A squared is 2A. How about B squared? Gone. 0. Okay, so that goes away. So plus 0. Now, how about this? 2AB cosine C. Well, notice there's an A and a C. Both are involved. The 2B is going to be a constant. So what rule do we have here? Product rule. So we're going to take the derivative of the first, so that's the A. Derivative of A is 1. So we have that constant 2B times 1 times cosine c. And now we're going to take the derivative of cosine c. So we have that 2ab, right? So it's the derivative of the first times the second plus the first and the derivative of the second. So we have minus 2ab. What's the derivative of cosine? Negative sine. And of c. Now, we're not done. We took the derivative of the outside, and we're taking the derivative not with respect to c, but with respect to a. But remember, c depends on a. So we say, okay, so what's the derivative of c with respect to a? And the answer is it's the derivative of c with respect to a, partial c, partial a. Okay. So, good news. We've now computed the derivative. Okay, so what comes next? Well, we plug in what we have. And we say, well, what do we have? We have a and b and c. So we say, okay, let's plug those values in. And, okay, so evaluate. We'll get 0 equals 2a, 2 square root 3, minus 2b, so 2 times 4, that's 8, cosine c, minus 2 times a times b, so minus 2 times square root of 3 times 4, that's minus 8 square root of 3, and there's a minus minus, that's a plus, and there's a sine of c, and then there's a partial c, partial a. And at this point, you're like, okay, cool. Well, wait, we aren't actually done. What about cosine c and sine c? We can't just leave them there. Okay, so we're going to do a quick aside. Okay, so here's our aside. And this is compute cosine c and sine c. All right, so here we go. What can we do? What can we do? Well, we have our original formula. So we say, okay, we know we have c squared equals a squared plus b squared minus 2ab cosine of c. So we start plugging things in. C squared, 7, equals a squared, 3, plus b squared, 16, minus 2ab, 2 square root of 3, and 4, and cosine c. Oh, okay, so let's see. 3 plus 16 makes 19, and then we can subtract, and 7 subtract 19 makes negative 12, equals negative 8 square root of 3 times cosine c. So divide, that says cosine of c is equal to, we have negative 12 over negative 8 square root of 3, and okay, well, we can certainly cancel the pause. 2 negatives make a positive. We have a factor of 4 we can cancel, right? So that's a 3 over 2 root 3. And, oh, well, hey, 3 over root 3, that becomes the square root of 3 over 2. I say, oh, well, that was really quite pleasant. So, update, this is square root of 3 over 2. That will probably be helpful. No, it will be helpful. What about sine of c? Now, there's 2 ways to do it. The one way to say, hey, I recognize this angle. This is a pretty nice angle. Do you recognize it? Cosine is root 3 over 2. That would be the angle of pi 6. And so sine of c would be sine of pi 6 would be a half. Now, if you don't remember that, don't worry. Or maybe you get a weird number. What can you do? Well, you just say, look, we know cosine squared plus sine squared is equal to 1. Now, cosine can be positive or negative, but because we're talking about the angle of a triangle, it's always between 0 and 180. Sine will always be positive. So what we do is we just plug it in. Cosine squared would be 3/4 plus sine squared equals 1. This says, oh, sine squared is equal to 1/4. Now take the square root. And again, you don't have to worry about plus or minus. It's always the plus. You get a half. So even if you get a number you don't recognize, you can still keep going. So 1/2. Okay, so we're doing great. All right, so updating. What do we have? We get, this is equal to, I'm going to slightly run out of space, but that's okay. We're almost done. Don't worry. I know we're almost out of space, but we're also almost out of problem. So 8 divided by 2 makes a minus 4√3. Yes, it does. Yes. 8 divided by 2 again, plus 4√3, partial C, partial A. Now, we can move the 2√3 minus 4√3 is a minus 2√3, move it across, and we end up with the following. 2√3, okay, so we move those to the other side, is equal to 4√3 times partial C, partial A. Now divide by 4√3, and what do we get? We get partial C, partial A is equal to 1/2. Ta-da! We did it! Woohoo! Nice! So this has some interesting things that have to happen to solve the problem. We have to use the original formula to figure out what's going to happen with cosine C and sine C, because that's going to show up. We have to think about, hey, when we're taking a derivative, treat C like it depends on A, use your chain rule, and use the product rule appropriately, and then evaluate. But doing all of that, we get a beautiful, beautiful answer. All right. Good job. Whew. All right. Let's keep going. Number 7. The surface defined by the function z, it's a function of x and y, square root of 9 plus 4x squared plus 3y squared. Wow, what a function. It contains the point minus 1, 2, 5. Find the unique vector v, a, b, so that the function f has 0 change at the point P in the direction of v. The magnitude of v is 2√13. Gradient, brain's getting ahead of ourselves. And a, this first entry, is positive. Okay, all right. Let's think about what we need. Well, let's start. There's a lot of words on this one. It says the function f has 0 change. So what should we be thinking when we see words like change? How something is changing. What is that really saying? And not only is it change, it's a change in a particular direction. And so we're like, oh, this part right here is telling us that the directional derivative is 0. So change is like the word rate. It's a clue. Think derivative. So we have that the directional derivative in the direction of v of the function f at the point P is 0. All right, so that's that first bullet point. And the magnitude being 2√13 just says at the end, make sure it has the right length. That's usually one of the last things we worry about. So we're going to save that one for the end. And similar, a greater than 0, we'll save that one for the end as well. Okay, so what do we have? Well, this is going to be the big clue. And indeed, if you get this, it opens the whole problem up. Now, how do we take directional derivatives? Well, that's taking the gradient of f at that point P dotted with our vector v so that we get 0. Okay. Now, technically, I see I made a little faux pas. So I'm going to fix myself. Now, notice here, v is not a unit vector. So we're going to say this is u, and so we say, just note, v is a scaled up u. So we're just going to make that little note there on the side. Okay. So what do we need? Well, the main part of this problem is to compute that gradient. And once we have that, we'll put all the pieces together. Life will be good. So we start by doing that. So we have our function. And before we do anything, let's make it calculus friendly. And by saying I want to make it calculus friendly, I'm going to rewrite it. So 9 plus 4x squared plus 3y squared to the power 1/2. All right, so step 1, find the gradient. So the gradient of f at a generic point xy is, well, it's going to be partial f, partial x, partial f, partial y. So that's just a reminder of what we're going to be doing. It's a vector, so we need a vector. So take derivative with respect to x. We're going to do chain rule, treat y like a constant. So 1/2. Then we're going to have 9 plus 4x squared plus 3y squared to the minus 1/2 times, that 4 better look like a 4, otherwise I'm going to get in trouble, times root of the inside, which is 8x, because we're taking derivative with respect to x, comma, partial f, partial y. Same process. All right, 1/2. 9 plus 4x squared plus 3y squared to the minus 1/2 times the root of the inside with respect to y, 6y. All right. Now, in both cases, they both have this expression 9 plus 4x squared plus 3y squared to the minus 1/2. We can actually pull that out in front if we want to. And for some reason, I want to. So this becomes 1 over the square root of 9 plus 4x squared plus 3y squared times, well, 1/2 times 8x makes 4x. 1/2 times 6y makes 3y. All right, good. Now, that's the gradient of f in general. Now we need the gradient of f at a specific point. So let's go ahead and do that. And, well, what do we have? The gradient of f at our specific point. Well, which point do we want? We want the point xy, which is minus 1, 2. So notice the p here. This is minus 1, 2, 5 is your x, y, z. We're going to actually take advantage of this. Notice, what does this tell you? It tells you that f of minus 1, 2 is 5. So that's going to be the square root of 9 plus 4 times negative 1 squared plus 3 times 2 squared. And you can check it out. 9 plus 4 makes 13 plus 12 makes 25. Square root of 25 is 5. So gradient of f at minus 1 comma 2 is, now, good news, we know this part is f, just downstairs, and it's 5. So you can plug it in, or you can say, hey, that becomes a 5. 1/5 times, and now we have here 4 times x, so that's a minus 4, and 3 times y, and that makes 6. All right. Now, let's talk about our direction. What has to be true is when we take the dot product, we have to get 0. Now, that's true for our unit vector, but if two things are perpendicular and you make one of those two things bigger, you scale up, it's still perpendicular, right? Scaling won't change the angle between the vectors. So here is our first great aha. We know the following. So if we take 1/5 times -4, 6 dot the vector AB, and this is u, we have to get 0 out. And, okay, so that's good. What does that tell us? Well, it says the following. Or -4/5 A plus 6/5 B has to equal 0. And, well, we can rearrange this. Or 4/5 A equals 6/5 B. And then you can just cancel the 5. And now the question is, you want to solve for A or solve for B? It doesn't really matter. Let's solve for one of them. Or we can say, look, A is 6/4. That's 3/2 B. Okay. Now, this is good. This is actually really good for us. What are we up to? Well, we now know the following. Our vector has a very particular form. Okay, so let's do it down here. Our vector AB looks like, I can replace A by 3/2 B, 3/2 B, comma B. And now what can we do? Well, we can actually pull out some term. So I'm going to write it as B over 2. So I'm going to pull out B halves. And if I do that, I get 3, 2. So this is the great, in particular, what do we have? Our vector has to be some multiple of this. So this is just saying some multiple, some scaling factor. And the good news is this entry is positive. So the only thing left to do is to say, well, what is that scaling factor? Okay, so we have a positive entry. We just got to make sure we get our scaling factor right. This having 0 change is already taken into account. So the last thing, when we'll work up here in this corner, what's the right scaling factor? Well, here we go. So again, this is our vector v. So we know that 2 square root of 13 is our magnitude of v. That's our assumption. But that's equal to the magnitude of b over 2 times 3, 2. Well, we'll just assume our scaling factor is positive. As some scaling factor, b is positive. Why does b need to be positive? Because we need this entry to be positive. So what is this? Well, the scaling factor just comes out. It's a positive times the magnitude of 3, 2. And what does this give us? Well, this is b over 2 times the square root. 3 squared, 9, and 2 squared is 4. Well, that is b over 2 square root of 13. Okay. But we already had a square root of 13. It's like we've lived a good, clean algebra life, right? And so we say, aha. All right, back down here. So we have 2 square root of 13 needs to equal b over 2 square root of 13. The square root of 13 is cancel. Move that across, we need b equals 4. Or really b over 2 equals 2. So we put that back in. And so we say, okay, so v, which is our a comma b, has to look like 2 times 3, 2, or it's 6, 4. All right. All right. Now, I know, even as I look at this, like, oh my gosh, there's a lot of stuff written down here. But actually, it's not too bad. What are the keys? Here's the big key. It all boils down to recognizing this. You need that the gradient dot the direction of v. So you can even put in v here. Gradient dot v has to be 0. And once you have that, that basically says, what does your vector look like? It looks like some multiple of a particular vector. Use the magnitude to figure out what the right multiple is, and then we put it all together, and you've got the answer. It's beautiful. Beautiful, beautiful, beautiful problem. All right. You can do these problems, right? You got this. You're great. All right? Okay. Well, a few more to go. Let's keep going. Number 8. Given that f of xy is g, u of xy, v of xy, use the information in the following table to find the values of f sub x of 2, 3 and fy of 2, 3. And you're just like, whoa, there's a lot of table there. And you might be getting a little bit nervous, but let's talk through the process. What's being used here? This is asking us about chain rule. You see, we have functions of u, which is a function of x and y, and v is a function of x and y. But in turn, g is a function of u and v. And so this says, okay, you got to know how the chain rule operates, and then you have to say which parts of the table do you need. They're giving you way more information than you possibly need. So this is saying, do you understand what you need to use? Okay, so first off, we begin this problem by drawing a chart. And I'm going to draw how things depend. So I say I see a g that depends on u and on v. A u depends on x and y, and v depends on x and y. Okay, so there's their chart. Now, on each edge of this chart, what do we have? Well, we have something above and something below. So it says the part above depends on the part below, which means that as I perturb this, this changes. And we can actually measure that. That's called derivatives. So I'm going to mark the derivatives that are associated with those changes. So g depends on u, so we can talk about g sub u. How does g depend on u? G can depend on v. U will depend on x. U can depend on y. V on x. And v can depend on y. So we've made our chart, labeled our edges, and now we're going to go and take our walks downstairs. So I can ask the question, how does g, which really at the outside is f, how does it depend on x? Because you'll notice there's an x in 2 locations. So you have to go down. So we have that f sub x, which, right, it's here. Well, we have how does g depend on u? How does u depend on x? So I like to think of this in some senses. How does x affect g through what's happening with u? But then, of course, we have a second path that involves x at the bottom. And we say, plus we have to take into account how does it get affected through v. So gv vx. Now that's our f sub x. Then we have to do our f sub y, right? Because we still have to do that. And we say, okay, well, there's y showing up down here. We say, okay, so again, we have our 2 ways to get down. So there's the effect that y has through the variable u, and there's the effect that y has through the variable v, right? gv vy, gu uy. Okay, that was the chain rule part. Now we have to be a little bit careful. This is very condensed. We've omitted some details. And so I'm going to be a little bit more explicit here. All right, so the first one, this fx of xy is g sub u, but g is a function of u and v. So I'm going to write u comma v. U sub x, u is a function of x and y, so x comma y. And then g sub v, well, g is a function of u and v, so uv. And then we have v sub x, xy. And same thing for the one below. F sub y of xy is equal to g sub u of uv, u sub y, xy, plus g sub v, uv, v sub y of xy. All right. Now, the pieces are in place. We just have to be slightly careful. We know what x and y are. That's given, 2, 3. So, if x equals 2, y equals 3, right, that's the 2, 3, then what is u? Well, u of 2 comma 3 is what? Well, that's where our table comes into play. We say, well, we have a u row, we have a 2, 3 column, so u of 2 comma 3 is right here, 3. All right, so we'll keep that in mind. So that's a 3. And v of 2 comma 3 is what? Well, again, we have a v row, a 2, 3 column, and so we say v of 2 comma 3 is right here, -2. All right, so we'll make a note of that, -2. All right, now, why did we do that? Because we need to evaluate. Okay, so once more, we're going to write this down one more time, but now we're going to plug it in. So what's going to happen? Everywhere we see an x, not the subscript, but these x's and y's on the insides, 2 and 3. U's and v's, u's are 3's and v's are -2's. And so we have the following. We have f sub x at 2 comma 3 is g sub u of 3 minus 2 times u sub x of 2 comma 3 plus g sub v of 3 minus 2, right, because I'm u and v, v sub x of 2 comma 3. All right. Now, underneath, we'll go ahead and do the same thing for fy. Fy of x comma y, so that's 2 comma 3, is g sub u of 3 minus 2. So g u 3 minus 2, u sub y of 2 comma 3. U sub y 2, 3. Then we have g sub v of u comma v, so that's g sub v 3 minus 2, v sub y of x comma y, vy 2 comma 3. All right. The good news is we've done the work. The rest of this problem is reading the table. So what are some things we need? We need to know g sub u of 3 minus 2. So there's a g sub u, that row, 3 minus 2, that column, and so we need to get that number, 4. So this is 4. And it's actually the same in both terms, 4 and 4. G sub v of 3 minus 2, so again, g sub v, 3 minus 2, so we need this entry here. So, say, okay, that is -3. All right, And we're almost there. We're in the home stretch. All right. We need u sub x at 2 comma 3. So u sub x at 2 comma 3, that's 4. So we'll put here a 4. And v sub x at 2 comma 3, okay, here we are. That's a 2. So we'll put a 2. And don't forget the plus. And we'll clean that up in a second. And but while we're at it, let's finish filling in the last entries. We have u sub y at 2 comma 3. So u sub y 2 3. That's our 3. So there's a 3 here. And then there's a v sub y at 2 3. V sub y at 2 3. And that's a 1. And so there's the 1. All right. Maybe we should have been marking these just so we knew what color corresponds to what. So we have our vy, vuy, here's our vx, here's our ux, and then we have our, I think this was our last one, our gu and our gv. That's coming in from these colors. Okay, right? It's all lining up. Okay, so we're really there, right? Don't worry, we're done. 16 minus 6 equals 10. 12 minus 3 equals 9. All right. These problems are meant to kind of make us nervous and maybe intimidate us. And I'm like, how can we do such a thing? But the point here, it's just a matter of making sure you have the right setup. And then figuring out, okay, now that I've done the work of getting the setup, how do I read the table? This is a learn to read the table type problem. And so you just have to go through and methodically, carefully, consistently work it out. You can do it. It takes a practice. Draw the tree. Use the tree to get the relationships. Be careful, right? Because it's very tempting to just, instead of using these values of 4, negative 3, to use these values of 3 and 2. And then it's like, your answer goes away. Be careful. Be methodical. Be patient. You got this. You got this. All right. Let's keep going. Number 9. Let f of x, y, z be a smooth function of 3 variables. Smooth is just another way of saying we can take derivatives. It's not what I would like to call it's nice. All right? So, good. We can take our derivatives. Let g of uv equal f of u cubed, u plus v squared, uv. All right? And let the point P be 1, 5, 2. Now, given gradient of f at P is 3 minus 1, 2, find g sub u of 1, 2. And you're probably thinking like, what? Wait, what's going on here? Okay, so let's see if we can't make some sense about what's going on. Now, we know a couple of things. So gu, now g is a function of u and v. So this is saying, you should let u be 1 and v should be 2. Saying, okay, all right. So we're trying to evaluate things. U equals 1 and v equals 2. All right, okay, that makes some sense. All right. Now, notice something here. 1, 5, 2. Well, let's try something out. Let's plug these in. What is 1 cubed? 1. How about this? What's 1 plus 2 squared? 5. What's 1 times 2? 2. So it's like, oh, so this point P is what happens when you plug in 1 in for U and V in for, 1 for U, 2 for V. Okay, so all right, that feels like we're on track. Now, some other things. We're told the gradient of f of P is 3 minus 1, 2. And so in particular, we have the following. We say, oh, what is the gradient of f? Well, we know gradient of f of P is partial f partial x at P, comma, partial f partial y at P, and partial f partial z at P. That's just how gradients work. It's the collection of partial derivatives. And so we say, okay, so that really tells us this first slot is the derivative with respect to x. This second slot, derivative with respect to y. And this third slot, derivative with respect to z, are 3 minus 1 and 2. So we know those partial derivatives. That's good. Now, we're almost there. What do we have? Well, we have functions in a function. Chain rule. Yes, this is a chain rule problem. You're probably going like, nah, but you should be like going, or hopefully like, there's a whole spectrum of feelings that people have when it comes to chain rule. And I'm not saying one way is the right way to feel about the chain rule, but I hope you grow to at least say, I got this. I'm confident in my abilities. So here's what I'm going to do. I'm going to start by saying I have my function f, which depends on x, y, and z. And now I look and say, well, what's going on? Well, we're saying that x is going to become u cubed. So x depends on just u. Y is going to be u plus v squared. So y depends on u and v. And z, well, that's uv. So again, z depends on u and v. Now, notice we're only asking for one partial derivative, g with respect to u. So we say, well, that's good. So we have the u down here, and that gives us 3 paths to tread. And okay, let's mark our partial derivatives along those pieces. We don't need to mark everything, just the ones that we need. We have fx, xu, fy, yu, fz, zu. So, our great putting things together says the following. We have that g sub u, so derivative of g with respect to u, is, well, it's f with respect to x times x with respect to u plus f with respect to y, y with respect to u, plus f with respect to z, and z with respect to u. Now, we're going to plug in our point. Before we do that, let's clean this up. Okay, so we have g sub u. I just want to point out something. What is derivative of x with respect to u? X is u cubed. Derivative of x with respect to u, 3u squared. All right, derivative of y with respect to u. Well, what's derivative of u plus v squared with respect to u? It is 1. All right, derivative of z with respect to u. Well, derivative of z with respect to u is v. So here we go. G sub u at 1, 2. This is going to be fx, and when you plug in 1, 2, you get the point 1, 5, 2. So fx of p times 3 times u squared. Well, 3 times 1 squared is 3. Plus fy, when you plug in uv, 1, 2, you get the point p. Right? We'll even make a note of it. We'll make a note. When u comma v equals 1, 2, then x, y, z equals p equals 1, 5, 2. So there's a little note for us to keep track. Okay, plus f sub z at our point p times v, but v is 2. Now you might say, but how do we get those? We already found them. They gave it to us. We just have to understand that they did. So here we have a 3 times 3 plus a negative 1 plus a 2 times a 2. Or that's 9 minus 1 plus 4, which gets us our final answer. 13 minus 1 is 12. All right, good. Oh, we made it. Now, this one is actually, if you understand what's going on, all the pieces are there. It actually is pretty clean. However, you got to understand how it all fits together. It's understanding that, this gradient, hey, that's giving us information about the partial derivatives. Okay, that when u equals 1 and v equals 2, that x, y, z is your point. And okay. And then, of course, fundamentally, you have to recognize that this is a chain rule problem. But once you do that, everything's there. Everything's there. We're not going to give you impossible problems. They might look impossible, but they're very possible. And we want you to do them because you can. You can. All right. We're almost in there. We're in the home stretch. Let's finish it up. One more to go. Our last problem, number 10. Given f of x, y, z is y squared plus the natural log of x to the 5th z cubed, use the identities between spherical and rectangular coordinates. Rectangular, by the way, is another way to say Cartesian, to express partial f, partial rho, partial f, partial theta, and partial f, partial phi in terms of rho, theta, and phi. Now, there's 2 ways you can do this problem. One is the way that is pretty quick and clean and not too stressful. And the other one is the way they want you to do it. Okay, so let's do them in both ways. And so I'm going to talk about the unintended way that they might want you to do this problem. Okay, so, but both of them have the same initial setup. You have to know how do you go between spherical and rectangular coordinates. And so you can say, well, we happen to know some facts. We know, for instance, that z is rho cosine of phi. We know that r is rho sine phi. And then if you combine that with x equals r cosine theta, y equals r sine theta, you get to the conclusion x is rho sine phi cosine theta, and y is rho sine phi sine theta. So this is hanging over everything. Okay, so method 1. So here's the strategy. We'll just briefly describe it. Is rewrite the function in terms of rho theta phi. So rewrite f in terms of rho theta phi. So that's the strategy. How do we do it? Well, so we're going to write f of rho theta phi is, now use these relationships to replace everything. So you get y squared. So that's rho sine phi sine theta quantity squared plus natural log of x to the fifth. So that's rho sine phi cosine theta to the fifth z cubed, which is rho cosine phi cubed. Now, before you jump in and finish doing it from here, simplify. Now, I'm going to do the following. I'm going to distribute the square through. Rho squared sine squared phi sine squared theta. Okay? Log. Now, take advantage of logs. If you have a log and you're going to be taking derivative, say, wait a second, hold on. Log has a way for us to pull things apart if there's multiplication going on. And there's a lot of multiplication going on. So we say, what can we do? Well, notice we have rho to the fifth, rho cubed. So that's rho to the eighth. So I'm going to have log of rho to the eighth. And I know I'm not done with that. I'll come through and do something more with that. Okay? Because log of products becomes the sum of the logs. Right? Log of a product becomes sum of logs. Okay, plus, there's only one sine phi, log of sine phi to the fifth, okay, plus log of cosine theta to the fifth, plus log cosine phi cubed. But we can, again, do what? Well, bring the 8 down, right? Powers come down. 8 log rho plus 5 log sine phi plus 5 log cosine theta plus 3 log cosine phi. This is our function in terms of rho phi theta. So now that we've rewritten things in terms of rho phi theta, we just have to take the partial derivatives. And it's okay. We don't have to rethink things from the ground up. We just say, all right, now just take derivatives, and we're just using different symbols. Different symbols doesn't mean we have to do different things. So what do we get? Well, we get partial f partial rho. And now take derivative anything with respect to rho. Well, there's a rho squared, so that makes it 2 rho. Everything else just comes along for the ride. It's a constant. So sine squared phi, sine squared theta. Here's a rho, so this will be plus derivative of log of rho is 1 over rho with respect to rho. 8 over rho, and nothing else. Okay, that was not bad. Partial f, partial theta. Okay, constant, there's something. Okay, so the 2 comes down, put that in front, 2 rho squared, sine squared phi, sine theta, times the derivative of sine, because we're doing chain rule, which is cosine theta. All right, that has no theta, that has no theta, that has a theta. So, okay, plus, what do we have here? We're going to get a 5. There's a fraction, and downstairs is a cosine theta, and upstairs is negative sine theta. And if we wanted to, we can say, well, that's 2 rho squared sine squared phi sine theta cosine theta minus 5 and sine over cosine. We can go ahead and write that as tangent. Okay. And our last one, partial f partial phi, is, okay, well, there's a phi there. So the similar idea, 2 rho squared sine phi cosine phi, and then sine squared theta. No phi there. This has a phi, so that's plus 5, write your fraction, sine phi downstairs, and the derivative of sine is cosine. That's not a phi. That's a phi. So plus 3. Downstairs goes to cosine. Upstairs, the derivative of cosine, negative sine. And, okay, so we can rewrite this as 2 rho squared sine phi cosine phi sine squared theta plus 5, I'll go ahead and write this as cotangent phi minus 3 tangent phi. And we're done. It's all there. It's all there. Okay, so that's method 1. So essentially it says rewrite the function and now take your partial derivatives. And essentially it becomes a problem about, do you know partial derivatives? Method 2. Okay. I got to go grab a piece of paper here. Don't worry. We have plenty of paper. It's all around us. It grows on trees. So before we get too far into it, I just want to emphasize what's the difference between them. So method 1 was rewrite f. Method 2 says we're not going to rewrite f. This is the method that they intended you to use. So method 2, and that is chain rule. Okay, so what's going to happen here? Well, we still have our x, y, z. So we should write these down. So we have x equals rho sine phi cosine theta. Y equals rho sine phi sine theta. And z equals rho cosine phi. And we have our original function. And I'm going to write that down as well. So we have our f of x, y, z equals y squared plus. Now, I'm going to take advantage of log here. So plus 5 log x plus 3 log z. Okay? It's the same thing we just did. I'm just doing it earlier. So we have our function, and we have our x, y, z. And now we're going to do a chain rule. So we'll put this off to the side. We'll bring it back and compare our answers. So what's going on? Well, we're thinking we have f. It depends on x, y, z. And x depends on rho, phi, theta. Y depends on rho, phi, theta. Z depends on rho and phi. So we have this chart. And we have all these partial derivatives, right? fx, fy, fz, x rho, x phi, x theta, y rho, y phi, y theta. It's getting so small we can barely read these. But we have all these partial derivatives. And now we just tie them all together. So what's going to happen? Well, let's start with partial f, partial rho. So if we're going to do partial f, partial rho, that would be, we're doing our rows. We're going to do f sub x times x sub rho, right? Plus f sub y, y sub rho, plus f sub z times z sub rho. Okay? And we say, well, we know these pieces. F sub x, well, take derivative with respect to x, that's 5 over x. X sub rho, all right, well, take derivative of x with respect to rho, and that's sine phi cosine theta. Right? Because it says right there, sine phi cosine theta. F sub y, well, come here. Where is f sub y? Well, the only y is there. It's 2y. And then y sub rho. And that would be sine phi sine theta. And then we come into f sub z, and that's a plus a 3 over z. And what do we have? Times that by z sub rho. That's a cosine phi. But we're not done, because this involves x, y, z in addition to phis and thetas. We have to get everything in terms of rho phi theta. So how do we do that? Well, we use what we have. All right, so what does this become? Well, we need to divide. Okay, so we need to divide by what we have. So we have x is rho sine phi cosine theta times sine phi cosine theta plus 2y, that's rho sine phi sine theta, times sine phi sine theta, right? Because this is your y, here's your x, plus 3 over z, rho cosine phi, times cosine phi. Well, okay, the cosine phi's cancel. Here, sine phi and cosine theta cancels. And, well, what do we have? We have a 5 over rho. Here's a 3 over rho. And that makes 8 over rho. Plus a 2, a rho. Then we have a sine squared phi and a sine squared theta. Okay, so that's partial f, partial p. And we're going to need more paper, but that's okay. But before we go to our next page, let's compare. Partial f, partial p, we said 8 over rho, 2 rho, sine squared phi, sine squared theta. They matched. Of course they're going to match, because we're still finding the same thing. We're just using different methods. And at this point, you're like, I prefer method 1, because we haven't even done 2 of our derivatives. That's okay. We have more paper. Okay, so next up, let's go for partial, dramatic pause. I'm picking a color. It's always good to make sure you get the right color, right? Okay, so next up we'll do partial f and partial theta. I'm feeling partial f, partial theta should be next. Okay, so just follow the way down, right? You got your thetas. And, oh, that one doesn't have a theta. Ha-ha! Whoa! That'll save us some work. Okay, so we have f sub x times x sub theta plus f sub y, y sub theta, right? fx, x theta, fy, y theta. Now, I think we can squeeze into this line. Take the derivative of f with respect to x, and that gives us 5 over x. Derivative of x with respect to theta, well, derivative of cosine theta would be a negative sine theta, so that's minus rho sine phi sine theta. F sub y, okay, derivative of f with respect to y, 2y. All right, so plus 2y. Y sub theta. Well, what's that? Derivative of sine theta is cosine theta, so that's rho sine phi cosine theta. But again, we're not done, because we got to get in terms of just rho phi's and thetas. We got to get rid of the x's and the y's. But we have x and we have y. So this becomes 5 divided by rho sine phi cosine theta times minus rho sine phi sine theta plus 2 rho sine phi sine theta times rho sine phi cosine theta, which becomes, and we'll do some cancellation here, the rho's cancel, does anything else cancel? Oh, whoops. I wrote this down wrong. That's a phi. The sine phi's cancel. And yeah, that's it for cancellation, but some is better than none. Sine over cosine is tangent, giving us minus 5 tangent theta plus 2 rho squared, and then sine squared phi, sine theta, cosine theta. All right, so how do we do? So let's pull up our chart to compare. Partial f, partial theta, we said minus 5 tangent theta, check. 2 rho squared, sine squared phi, sine theta, cosine theta. Yes, we matched again. Oh, nice. Okay. Whew. Now, once more to the breach, dear friends. Once more. We've got to get the phis. Our last one. Partial f, partial phi is f sub x, x phi, plus f sub y, right, fx, x phi, fy, y phi. We're using our chart, fz, z phi. All right, now, we know these pieces. fx, all right, come here. Derivative of f with respect to x, 5 over x. It's consistent. That's not surprising. X sub phi. Well, there's only phi right there. Derivative of sine is cosine. Everything else comes along for the ride. So rho cosine phi, cosine theta. Now, f sub y. Well, we've already done it, but again, derivative of y squared is 2y. So plus 2y. And y sub phi. Well, the only phi there is sine. Derivative of sine is cosine. So rho cosine phi, sine theta. And f sub z. Well, derivative of f with respect to z is a 3 over z. Z with respect to phi. All right, derivative of rho cosine phi with respect to phi is going to be a minus rho sine phi. All right. So, this becomes, we have to put everything in terms of rho phi theta. That was the instructions. 5 over rho sine phi cosine theta, rho cosine phi cosine theta, plus 2 rho sine phi sine theta. That's the y. Don't forget, you still have to have that term there. Rho cosine phi sine theta, plus 3 over z, 3 over, not z, rho cosine phi, sorry about that, times minus rho sine phi. All right. Okay. We're in the home stretch. Now, we've already done this problem once. So this is really, we're really in the home stretch. The rows here cancel. The rows here cancel. The cosine thetas there cancel. So that's good. What's left? Well, we have cosine over sine, making it cotangent. Here we just have to multiply. We have a rho squared, a sine phi, and a cosine phi. All right. And then we have a sine squared theta. Here, there's a minus 3. We have sine over cosine, making it tangent. Okay, so pulling it up. Let's check. Did we get it? 5 cotangent phi, good. 2 rho squared sine phi, cosine phi, sine squared, and a minus 3 tangent phi. Okay. Whew. That's a lot of work. Oh, but I chose one that was a little bit harder. All right. You'll see something a little bit simpler. But the point is, you have options. And think about what you're asked to do and think about what's the best way to approach it. And sometimes, some methods will be a little bit simpler, and sometimes others will be. And So think about it. It's okay to take a moment to reflect before you jump into a problem and say, okay, you know what? I love myself and I want the best. So let me do something that's nice to myself. You deserve to be kind to yourself. I like you. And I want you to do well. Thank you for working hard. Please keep at it. Keep doing the work. It's going to come. I believe in you. All right. Well, thank you again for joining, and I hope I'll get to see you soon. Bye.